So now we've seen the precise definition of lists. Let's see some more representations of lists, some more useful representations. So we saw the EBNF rule. This gives already one textual representation. So what we do is we start with the left-hand side of the grammar rule, angle bracket list, angle bracket int, and we replace repeatedly each left-hand side by one of the possibilities of the right-hand side. So for example, list int can be replaced by 10 bar list int, and so on, relist int again by 11 bar list int. Eventually we can replace the list int by nil, and then there are no more left-hand sides, so we have a list. So that's one textual representation. In Oz, we have another textual representation, which is called the bracket notation, using these rectangular brackets enclosing an element. So this is used for a non-empty list with greater than 0 elements. And what it means is that this representation in blue is identical to the grammar representation, which is the only one that we are going to actually reason about and give semantics to. So bracket 10, 11, 12 is identical to 10 bar, 11 bar, 12 bar nil. And if you write them in the OS system and you do a comparison with equal, equal, it will say true. For the system, those two are identical. No difference. So it's purely a syntactic comfort for the programmer who likes to write lists in the bracket way. So, in fact, there's a name for this kind of comfort. It's called a syntactic sugar. Syntactic sugar allows you to make different textual representation of the same thing. And just like sugar is not usually good for you if you eat too much syntactic sugar is not good for the clarity, but a little bit is good. Another representation of lists is a graphical representation, as a graph, a drawing. So a graph with nodes and edges. And this is very important because human beings have a very powerful visual reasoning. So for many people, myself included, maybe you too, this is a very useful way of representing lists. So let me show you how it works. We start again from some left representation here. For example, 10 bar list int. And we draw 3 nodes. So we draw a node with the vertical bar, we draw a node with the 10, and then a node for the other part here, which list int, which is then replaced further by parts of the grammar rule in the same way. So there are arrows here, edges with arrows between the nodes, and this gives us a graph representation. So this structure here is actually a special case of a more general structure called a tree, and trees are, next to lists, the most important compound data structure in computer science. So I will now define what it is, a tree. So a tree is either a leaf node, so an element like nil with nothing more attached, and this is called an empty tree. Note like nil is an empty list. Or a tree is a root node, a node which is not empty, which has trees attached to it, which are called subtrees, a certain number. So this is a tree. Notice that lists are a special case of trees. A binary tree is a tree where all the root nodes have exactly 2 subtrees. So as before, the leaves have no subtrees, and the non-leaf nodes, which we call the roots, have 2 subtrees. So other forms of tree are possible too, and there's many, many, many variations. But in this course, we will show some very nice algorithms on binary trees in a later lesson.